All right, welcome back to another calculus lecture. So in today's lecture, what I want to do is kind of go back to some more conceptual thinking. In our last few lectures, we've been doing a lot of computations with derivatives and just sort of how do you actually compute these things. And now what I want to do is return to something that we sort of touched on when we first introduced the derivative, but this is the idea of the tangent line being a good approximation of a function. So the first thing that I want to do is just define the tangent line approximation. So definition. So if f of x is differentiable at the point x equals a, the tangent line to f of x at x equals a is given by the following. So maybe we'll just say this is L of x for the tangent line. This is equal to, well, we know that the slope of the tangent line is the derivative, and then we use the point slope formula and write it like this. So it's the slope of the tangent line, so the derivative evaluated at a times x minus a plus the function evaluated at the point a. And we've sort of seen this before, and in your homework I've had you compute this equation using the point slope formula. And the thing that I want to note, maybe I'll switch colors here. So the idea here is that for x close to a, and close in a very sort of non-rigorous way, just for x close to a, so maybe within 100th or a 1000th of a or something like this, L of x should be approximately f of x. These things should be pretty close. They're not going to be exact, but we expect that the tangent line approximation is close to the actual true value of f of x. And we're also going to call L of x, so call L of x the linearization of f of x around a, around the point x equals a. So that's why we choose an L for this, because we're really saying that we're going to take the function f and make it look linear, i.e. it's going to be a linear function, and that should do a pretty good job of approximating f of x around the point x equals a. Okay, so let's do a few examples of just computing some of these tangent line approximations, or these linearizations. So example, compute the linearization, which is really just a tangent line, linearization of f of x, of sine of x around the point x equals 0. Okay, so if I want to compute this linearization, what do I need? Well, I need my derivative, and then I need to evaluate it at 0, and I also need to evaluate my function at 0. So we have that d dx of sine of x. Well, we know that's cosine of x. We know that sine of 0 is equal to 0, and cosine of 0 is equal to 1. And so the linearization is, well, L of x equals the derivative evaluated at 0. So the derivative here evaluated at 0 is going to be 1, so I won't even write that. And then I have x minus, well, my point a, which is 0, or maybe I will write this, 1 times x minus my point, 0, plus the function evaluated at 0, so 0. And this is just x. Thus, for x approximately 0, we have that sine of x is approximately x. Okay? And so if you wanted to compute sine at a number close to 0, then you can really just take it to be that number. So, for instance, sine of 0.01 is approximately just 0.01 itself. I don't have to, if I wanted a pretty good approximation of this quantity, I can just use 0.01 because my linearization is telling me that sine of x is approximately just x when x is very small, and 0.01 is, of course, very close to 0. Okay, so there's one example. Maybe let's do another one. So example, compute the linearization of e to the x around the point x equals 0. So my a is again going to be 0 in this case. Well, what do I need? I need the function evaluated at 0, and I need the derivative evaluated at 0. So we know that the derivative of e to the x is just itself, it's e to the x. And e to the 0 is equal to 1. Anything to the power of 0 is equal to 1. So the linearization is, well, L of x is equal to the derivative evaluated at 0, so 1 times x minus 0, plus the function evaluated at 1, which happens to coincide with the derivative. And so this is x plus 1. Thus, e to the x is approximately just 1 plus x for x near 0. Okay? And so if I wanted to compute, so for instance, e to the 0.01 is approximately just 1 plus 0.01, which is 1.01. So if I wanted to estimate e to the x for x very close to 0, it suffices to just use this approximation. And I'm really not going to do too bad in my approximation. Okay? So maybe as another example, yeah, we'll do one more example of this. And this time we're actually going to figure out what our function is and what our point is from just the context of the problem. So one more example. So use a linearization to estimate the square root of 16.2. Okay, so I've got this square root function. I'm taking the square root of 16.2, and I want to know, okay, about what is that? I don't need to have the exact value. I just want a pretty good approximation of it. So we want to use a linearization, so we're going to need a function. Well, what's the function that we're really dealing with here? So let's let f of x just be the square root function. We're really just taking the square root of a number. And then sort of what's the point around which we want to linearize? Well, the point that we want to linearize around is going to be a point that we can evaluate f of x at. Well, I can take the square root of 16 easily enough. It's just 4. So let's linearize around the point a equals 16. So then f prime of x is equal to, well, if we want to differentiate this, this is just x to the 1/2. So I'm going to get, this is the derivative of x to the 1/2. And by the power rule, this is 1/2 x, 1/2 minus 1 is negative 1/2. So there's my derivative. And now I need to evaluate it and my regular function at the point 16. So f prime of 16 is 1/2 times 16 to the negative 1/2. When I raise something to a negative power, I just divide by that thing. So this is really 1/2 times 1 over the square root of 16. And so this is 1/2. Square root of 16 is 4, so this is 1/4. And so this is 1/8. And likewise, f of 16 is just 4. So the linearization, hard word to spell, nice big word, is L of x equals, I take my derivative evaluated here. Well, actually, maybe let's write it out just to be very explicit about what we're doing here. And so the derivative evaluated at 16 is 1/8. And then I have my x minus 16. And then my f of 16 is just 4. Okay, now we could expand this out and write this in the slope-intercept form, but I think it's actually easier to do it like this. So we've got our linearization, and now what do we want to say? What do we want to say is that the square root of 16.2 should be approximately L of 16.2, right? 16.2 is pretty close to 16, and so the linearization should be doing a good job of approximating this function. So what is L of 16.2? Well, this is 1/8 times 16.2 minus 16 plus 4, which is 1/8 times 16.2 minus 16 is just 0.2 plus 1/4. And 0.2 is just 1/5, so this is 1/8 times 1/5. You could just do this on a calculator if you wanted to do it more quickly. But this is equal to 4 plus 1 over 40. Pause the recording there just to do a quick calculation. This is 4.025. And if we wanted to do the actual value of this, just to see how close we were, the actual value is 4.02492 repeating, or whatever. They're not repeating, but there's more decimals here. So you can see we actually did a pretty good job. If we were to round this at the third decimal place, we would get precisely what our estimate is. And so this linearization, this tangent line approximation, is actually doing a pretty good job of approximating our function. Okay. So maybe let's talk about this from a more general sort of standpoint. So let's let e of x be the error in the linearization approximation. Be the error in approximating f of x by L of x. And we can just write down what this is. E of x is equal to, well, f of x, and then I'm going to subtract the tangent line approximation, or the linearization, around this point. So I'll just write it like this, and then this is f of x minus, and what was L of x? This is f prime of a times x minus a plus f of a. And if we distribute the negative, this is f of x minus f of a. If we just write this first, and then minus f prime of a over x minus a. Okay? So all e of x is, it's just capturing what the difference is and using our function versus our linearization. And if we go back to the previous problem with that, the square root of 16.2, the f of x would be the square root of x, and L of x would be the 1/8 x minus 4, or x minus 16 plus 4. Okay? So there's maybe something to say about this, and that is that as x approaches a, as x gets very, very close to a, this function does a very good job of approximating, or this relative to the distance x minus a goes to 0. That is, L of x is a very good linear approximation of f of x. So that was perhaps a little clunkily said. So what I want to say here is that we have a theorem which we can prove very quickly, and that is that the limit as x approaches a of e of x over x minus a, this is equal to 0. Okay, so let's go ahead and prove this. This is actually very simple. So if I want to do this proof, let's just write down the limit computation. So the limit as x approaches a of e of x over x minus a, let's write down what e of x is. This is the limit as x approaches a of f of x minus f of a minus f prime of a times x minus a, all divided by x minus a. This is equal to, let's split this up into two limits. I've got the limit as x approaches a of f of x minus f of a over x minus a. And then minus the limit as x approaches a of f prime of a times x minus a divided by x minus a. Well, what is this first guy? This is the literal definition of the derivative. So this is f prime of a. And then notice what we have here. We have the limit as x approaches a of, cancel out these guys. We're not at the point a during the limiting process. So this is just f prime of a. This no longer, it depends on x. And so what do we have? This is f prime of a minus f prime of a, because the limit of a constant is just the constant itself. And this is equal to 0. Okay? So maybe let's look graphically at what this says. You know, we've just written down this theorem and stated this limit, but what is this actually communicating to us? So through the magic of video editing or you know, things like this, let's look at some of these functions that we've talked about. So here I've got the blue line here is the function sine of x, and the yellow line is its linearization around the point x equals 0. And notice that as I zoom in on this graph, look what happens to the blue line. It starts to almost coincide with the yellow line. And when I get very close in, you can't even tell the difference. The blue line has vanished. It's completely being, it's almost coinciding exactly with x, so much so that we can't even tell the difference. And so what differentiability really means, the fact that a tangent line even exists, so if a function is differentiable, then it has a tangent line, and if it doesn't have a tangent line, then it's not differentiable. Differentiability is really saying that you can get a pretty good linear approximation. And maybe let's go to another example. So e to the x, we saw that its linearization was this 1 plus x. And as I zoom in around the point 0, notice what happens. Again, e to the x basically just coincides with this 1 plus x. As I zoom in further and further, my graph just looks like a line. It's laying almost perfectly on top of this 1 plus x. And if I were to keep zooming in, that would just that trend would continue. And so maybe let's take a look again at what this limit is saying. This limit is saying that as x approaches a, so as I zoom in closer and closer on my graph, the error in using my tangent line approximation, my linearization L of x, in place of f of x, the difference between those is going to 0 relative to the distance between x and a. That is, relative to how close I am to my point, the error in using my linearization in estimating f of x, that error goes to 0. Okay, so this is the idea here, and it really communicates, I think, what differentiability means. So, differentiability means that you have a good linear approximation. So differentiability implies that we have a good linear approximation. And conversely, the absence of a good linear approximation, i.e. the absence of having a tangent line, implies that we're not differentiable. Implies that our function is not differentiable, or implies a lack of differentiability. Okay, so differentiability, we've talked about it as smoothness in a graph before, and we've talked about it with some other lenses as well, but here it's really saying that differentiability means you have a good linear approximation. If you zoom in close enough, you just look like a line, like this linearization here. And in your homework, I'll actually detail with a few different problems that this linearization, this good linear approximation, is in fact unique. It is the only good linear approximation. Okay, so that's everything for this video, and I will see you all in the next one.